In this video, we'll be discussing polarization and polarizers. This is a fairly different topic from everything we talked up to this point. Up to this point, we've talking about wave effects of light and talked about interference effects, either due to two sources or three or four or five, so diffraction issues, or due to reflections. This is entirely something separate. This is a non-ray property of light, so it's not just that it travels in a straight line, so this is something new. But this is related to the fact that it's an electromagnetic wave, not that it's just any old type of wave. We just mentioned polarization fairly briefly in our discussion of electromagnetic waves, and I just sort of said, oh, here's what it is, we'll get back to it. So I'll remind us a little bit about what polarization is. The idea is that in an electromagnetic wave, the electric field is going to vary in a particular direction. In this picture, it's horizontal. It becomes left and then right and then left and then right. And the magnetic field is up and down and up and down. Now, we need some sort of direction that indicates that orientation. The electric field is becoming left then right, then left then right. It's not becoming up then down. That direction is called polarization. Now, note that it's not really a vector. Because the electric field is right, and then it's left, and then it's right, and it switches back and forth, that direction we want to describe is left-right, not left or right. Okay? We want an axis, just like you have like a vertical axis and a horizontal axis on a plot. And the vertical axis and the horizontal axes aren't up or down, they're up and down. And polarization in that same way is up and down, or left and right, not just left or right. And note that this direction is perpendicular to the direction that the wave actually moves in. The picture we had of light before is polarized light. Now, there's something called unpolarized light. And I think that the term unpolarized is somewhat confusing. It's not like there's an electric field and there's no direction of the electric field in this electromagnetic wave. Instead, what it is several of these waves all overlapping each other, and the electric field varies in all different sorts of ways, meaning that there are all sorts of different polarizations all stuck on top of each other, and that's what I'm trying to show you here. So here's a single wave. Here is a bunch of different polarizations all sitting on top of each other. So you have a blue wave, you have a green wave, you have a red wave. All of these are the equivalent of the red in here, just showing you the electric field at all different angles. And if you view it edge on, I'm going to try to show it by something like this, where these arrows are the polarizations, the direction in which the electric field is varying, maybe up and to the left for one moment and then down and to the right. And since they're all on top of each other at once, what you find is that there's sort of no preferred direction the electric field is varying in at the moment. It just sort of wiggles all around in random directions. And most light sources produce unpolarized light. So if you turn on your incandescent light bulb, it's unpolarized. If your LED, most devices and most ways of making light produce unpolarized light. So most light you see is unpolarized. Now I want to talk about a second topic that's related, which is something called a polarizer. A polarizer is a device, or really a material. And a polarizer is a material that interacts with light in a very specific way. And the specific way it interacts with light is to only transmit light if the light has the correct polarization. That it only lets a particular polarization through the polarizing material. So say before I have unpolarized light, and the light is traveling from left to right. The direction the electric field varies is going to be like up, down, or left, right, or something along those lines, which I'm trying to show with these red arrows. This is my attempt to be a 3D. The polarizer only allows it in the direction it calls the transmission axis, which in this case I'll take to be vertical. So the light beforehand might have polarizations in all directions. The light afterwards only has light in the same direction as the transmission axis. And so the way that it's said is that it polarizes light. So unpolarized light becomes polarized light as it goes through a polarizer. Okay? Now, here's the way you want to think about this working. Let's say this black arrow is the direction of a original light. Let's say we have polarized light that is in some angle, like this tilted sort of 4 to 5-ish degree angle, meaning the electric field is up to the right, then down to the left, then up to the right, as it's coming towards your face. And you put a polarizer between your face and the light source. And the transmission axis of the polarizer was up-down, so it's only going to allow up-down. What happens to the light as it goes through? Well, it doesn't block it, because you can think of an electric field that's up and to the right as both being left-right and up-down at the same time. That really being two different electric fields, an vertical electric field and a horizontal. It blocks out the electric field that is horizontal and transmits the electric field that's vertical. So any angle other than perpendicular to the transmission axis will make it through, but just to more or less of an amount. So what happens if you have unpolarized light shine through a polarizer? Well, since there's all sorts of different polarizations, a lot of it's going to get blocked. And that's going to make the light dimmer. And actually, specifically, it makes it half as bright. The intensity is half as bright after the polarizer as before. So when you go from unpolarized to polarized, going through a polarizer, it drops the brightness by exactly a factor of a half. Now, the other thing that it does is that it causes it to be polarized. The light afterwards is entirely polarized in the direction of the transmission axis. On the other hand, if you have polarized light, perhaps light that has already gone through another polarizer, that goes through a new polarizer, it also becomes dimmer. Some of the light is blocked and some does not transmit through. But it isn't as straightforward as a factor of 2. The dimness goes down by a formula that's called Malice's law. And that says that the intensity after it's gone through the polarizer is equal to the intensity before times a factor, and that factor is cosine squared of the angle between the transmission axis and the polarization axis, so the polarization of the incoming light. If they're in the same direction, then that angle is 0, and cosine squared is simply 1. If they're perpendicular to each other, so they're not at all in the same direction, then cosine squared would be of 90 degrees is 0, and so none of the light makes it through. So this is a formula that gives you precisely how much light makes it through if you have polarized light striking a polarizer, and it goes somewhere between entirely the same amount of brightness to entirely dark. All of the light makes it through if it's in the same direction, none of the light makes it through if it's perpendicular. Now the other thing is that after it goes through the polarizer, its polarization is now in the direction of the transmission axis. Okay? So it's now reoriented itself.